So this is how our table is going to look like. We have the joints, that is joint A, B, C, D, and E, which we have all written there. Then we have the spans. For the joint A, we have span A, B. For the joint B, we have two spans, BA and BC. BA, BC. For span C, we have CB on the left and CD on the right. For joint D, we have DC on the left, DE on the right. And for the joint E, we got ED on the left. Then from there we have the distribution factors. We had already calculated them and we have written each of them on the required position. Same case with the fixed end moment. So the first thing we are going to do, since B beyond B, that is on the left hand side of B, the member BA is overhanging, we are going to balance B. And remember, we are balancing because the anti-clockwise, the sum of anti-clockwise moment and clockwise moment is not equal to 0. And for a joint to be balanced, anti-clockwise moment and clockwise moment, the resultant of their sum must be 0. So when we look at the joint B, on the left hand side we have an anti-clockwise moment of 4.00 kilonewtons meter and a clockwise moment of negative 6.25. So we have an unbalanced moment, and therefore we must balance that. And how do we balance? First of all, for us to get the excess moment, we are going to change signs. So positive 4 will change to negative 4, and negative 6.25 will change to positive 6.25. And that is going to give us positive 2.25. And then we are going to distribute this positive 2.25 on each member using the distribution factors. So for BA, we are going to have 0 times 2.25, which is 0. And for the member BC, we are going to have 1 multiplied by 2.25, which is positive 2.25. Now, after balancing B, the next thing we are going to do, we are going to carry over. So we carry over half of this moment to the joint C. So half of 2.25, that is 1.13. So we are going to have positive 1.13. That is when we carry over half of this moment. There, remember, the carryover factor is usually a half. Then from there we are now going to have the initial moments. So we write here initial moments. Let me write in short form, initial moms. So let's have a separation at this point. Very good. Now, the initial moments are going to be as follows. Here we are going to have a 0 since we don't have any moment on that line. Then this one we are going to have 4 plus 0, that is 4.00. This one is going to be negative 4.00. And now our joint B is balanced. The resultant bending moment is 0. 4 minus 4, that is 0. And then here we are going to have 6.25 plus 1.13, that is 7.38. And then this one is going to be 11.25. Then this one is positive 11.25. We got negative 6.25. And here we got positive 6.25. Then after that, we are going to distribute. So we write there. Distribute. So here we got a 0, and this is going to be 0 since 4 minus 4, that is 0. Now, for the joint C, the moment is unbalanced. So we have an excess moment of, we change signs, so this is going to be negative 7.38 plus 11.25, and that's going to give us positive 3.87. So that is equals to positive 3.87. Then that positive 3.87 we are going to distribute on each member using the distribution factors. So on the member CB we are going to have 3.87 times 3 divided by 7, which is going to give us positive 1.66. On the left hand side, that is CD, 3.87 times 4 divided by 7, that's going to give us a positive 2.21. Positive 2.21. Then on joint D, we have an excess moment of how much? So this is going to be negative 11.25 minus 6.25 will change to positive 6.25, and when we do so we are going to get negative 5. So that is negative 5. That negative 5 we are going to distribute it using the distribution factor. So on the left hand side we are going to have a half multiplied by that excess moment of negative 5, which is negative 2.5, and for the member DE the same, a half times negative 5, that is negative 2.5. Then here we are going to have a 0. Then after distributing, the next thing will be carrying over. So we carry over. And how are we going to carry over? We are going to carry over half of this 2.21 kilonewton meter. We carry it to the joint D. So this part we are going to have half of 2.21, we are going to carry it over here, and that is going to be positive 2.21 divided by 2, that is 1.10. So that is positive. In the same way, we carry the half of 2.5 on the joint C will be negative 1.25. So we got that. Then in the same way, we carry half of negative 2.5 from joint D, we carry it to joint E, and definitely that is negative 1.25. So we are done with carrying over. Let's write a 0 there, and the other parts we also write zeros. Then after carrying over, the next thing will be distribution. So we distribute again. Coming here, we have an excess moment of positive 1.25. So remember, we said that whenever you are calculating the difference in moments, you change sign. So this is going to be 0 plus 1.25. So at this point, we are going to have 1.25 times 3 over 7, which is going to be positive 0.54. Positive 0.54. Then positive 1.25 times 4 over 7, that is going to be plus 0.71. Then coming at this point, the excess moment is negative 1.10. So half of it here we are going to have negative 0.55, and on the member DE we are going to have a half times negative 1.10, which is negative 0.55. Then we input zeros on the other parts. Then after distributing, the next thing will be carrying over. So we carry over, and we are going to have this Half of 0.71 will be carried over to joint D, and that's going to be positive 0.36. So here we got plus 0.36, which is half of 0.71. Then half of 0.55 will be carried over on the joint C, and that's going to be negative 0.28. So that is when we carry over there. And then we do the same on this side. We carry half of 0.55 from joint D to joint E, which is going to be negative 0.28. After carrying over, we distribute again, since we haven't yet reached to the required degree of precision. So distribute. The other parts on the carryover part are going to be zeros. For distribution, we have an excess moment here on joint C of positive 0.28. So this positive 0.28 on member CB, we multiply by the distribution factor. So 3 over 7 multiplied by positive 0.28, that is going to be positive 0.12. On this side, 0.28 times 4 over 7, that is going to be positive 0.16. Then here on joint D, we got an excess moment of negative 0.36. You change sign. So half of distribution factor on DC is a half. So half of 0.36, that is negative 0.18 after changing sign. The same case here, since the distribution factors are the same. So 0.18. And then the other parts, we input zeros. Then after distribution, the next thing will be carrying over. So we carry over half of 0.16 from joint C to joint D, which in this case will be positive 0.08. So that is when we carry half of 0.16 to joint D. Then we do the same, carry over half of 0.18 to joint C, and that's going to be negative 0.09. So that is when we carry half of 0.18. We do the same on this side. We carry half of negative 0.18 to joint E, and that's going to be negative 0.09. So that's what we got. Then the others, we input zeros. So that is the part of carry over. So carry over. After carrying over, we distribute. That is always the procedure. Distribute, carry over. Distribute, carry over. Distribute, carry over. Until we reach the required degree of precision. So we distribute. And come to joint C. The excess moment is positive 0.09. Change sign. So distribute. Multiply 0.09 by 3 over 7, and that is going to give us a positive 0.04. Then positive 0.09 multiplied by 4 over 7, that's going to be positive 0.05. Then we come to the joint D, and the excess moment is negative 0.08. You change sign. So half of negative 0.08, that is negative 0.04. On the member DE, the same, negative 0.04, since the distribution factors are similar. And then the other parts, we are going to input zeros. Then finally, after distribution, we can now look at our final results and see that we have now the required degree of precision. That's what I think. We now have the required degree of precision, so we don't need to carry over again. So what we are going to have now are the final moments. So here we are now going to have final moments. Final moments. And for the final moments, what we are going to do, we are going to add light from the initial moments. That is where we are beginning our addition. So, on the member AB, we are not going to have anything. That's going to be 0. On the member BA, we are going to have positive 4.00. On member BC, we are going to have negative 4.00. On the member CB, when we add from 7.35 all the way to 0.04, we are going to get positive 9.74. The same case on this side, from negative 11.25 all the way to positive 0.05, when we add all this, we are going to have negative 9.74. On the joint D, for the member DC, from positive 11.25 to negative 0.04, that is going to be a positive 9.52. And on the member DE, that is going to be negative 9.52. Then finally, for the joint E, from positive 6.25 all the way to negative 0.09, that is going to be positive 4.63. So those are now our final moments which we are going to use to plot the BMD. But before we go, we plot the bending moment diagram, we are going to calculate the bending moments due to vertical loads. So here we have bending moments due to vertical loads, and we are going to begin with the span BC. So for the span BC, the maximum bending moment will be given by WL squared divided by 8. And in this case, W is 3 kilonewtons per meter. The span B to C is 5 meters, therefore that is 5 squared, and then we divide this by 8. We divide that by 8. And when we do so, we are going to get a maximum bending moment of 9.38 kilonewtons meter. So that is the maximum bending moment for the span BC. For span C to D, the maximum bending moment will be given by WL squared divided by 8, that is due to the uniformly distributed load between C and D, plus due to the point load, the bending moment will be given by WAB divided by L. So that's what we are going to have, and this will result to WL squared. W is 3 kilonewtons per meter, so 3 multiplied by the span is 5, therefore 5 squared, divide this by 8, plus W, that is the point load of 8 kilonewtons, so 8 multiplied by A is C to F 2.5, so 8 multiplied by 2.5 multiplied by B 2.5, and then we divide this by L, which is 5 meters. And when we do that, we are going to get a maximum bending moment of 19.38 kilonewtons meter. So that is the maximum bending moment on the span C to D. Good. Then the final span is the span DE. Therefore, for span D to E, the maximum bending moment will be given by WL squared divided by 8. since it is loaded with the UDL, and this will be 3, the UDL, multiplied by the span 5 squared, and then we divide that by 8. And when we do so, we are going to get a maximum bending moment of 9.38 kilonewtons meter. So we now have all the moments we need to plot the bending moment diagram, and we are going to begin with the bending moments due to vertical loads. Let's begin with the maximum bending moment between span B and C, that is 9.38. So 9.38, let's get that point. And this is going to be a smooth curve since the span is loaded with a UDL. So we got a smooth curve. Good. Then on the span C to D, we have 19.38. It is also going to be a smooth curve since it is loaded with a UDL. So we got a smooth curve. I hope that is a smooth curve. Yep, something close to that. And then for the member DE, a smooth curve of 9.38. So we brought another smooth curve, maximum 9.38. Then we drop it there. Boom. So that's what we got. So I'm now going to write the value of each bending moment. We have 9.38 here, so 9.38 kilonewtons meter. This one is 19.38 kilonewtons meter, and this one is 9.38 kilonewtons meter. Then after plotting the bending moments due to vertical loads, we are now going to plot the bending moment due to supports, due to support moments. And at A, that is the bending moment is 0. At B, we have 4. So 4 about that point. So join 4 to 0 there. So this is 4. Let me write it with green color. So we got 4 kilonewtons meter. And then the bending moment at C, that is 9.74. Few units above 9.38. So I'm going to join this to 4. Yep, I think that is awesome. So this is KNM. This one is 9.74 kilonewtons meter. Then we got the bending moment at D, which is 9.52. So 9.52 somewhere there. So I join that to, yep, exactly. So this is 9.52 kilonewtons meter, that point. And then the bending moment at the joint E, 4.63. So 4.63 just above 4. So again at that point. So got it there. So I'm going to join this 9.52 to, yeah, to 4.63. So let me write it this way. 4.63 kilonewtons meter. This is a negative, positive, negative, positive, negative, and positive. And then finally, I'm going to shade off the outline of my BMD for it to become very clear, very smart, and awesome. Yep. So ladies and gentlemen, that is how our bending moment diagram is going to look like. And please, ladies and gentlemen, please subscribe to this channel for more and more structural engineering calculations. So we are done, and we appreciate so very much for you staying there and watching our video. We appreciate so much. So Let's meet in yet another lesson. No, sir.